All righty. Make sure I got the right papers. So today we're going to be looking a little bit at the Pythagorean Theorem and also its converse. All right, but first, before we do that, we're going to talk a little bit briefly about simplifying square roots, okay? Because we're going to be dealing with square roots in, the Pythagorean theorem and stuff like that. And while sometimes we have our calculators, sometimes we don't, and we still need to be able to simplify square roots and kind of work and do arithmetic with those without our calculators and stuff. So we're going to jump first into simplifying square roots. Okay, and really should just be a refreshing of your memories, I hope, okay, from the past. And then we'll talk about the Pythagorean theorem and its converse. Okay, we're pretty good with the Pythagorean theorem, but I also want to go over its converse too. Okay, so question is, right, how do we simplify square root of 25? We'll start with an easy one. Okay. We all know the answer to this is what? 5, right? Okay. But let me kind of take you through some little steps with this, right? So, well, we could just say it's just equal to 5, right? Or we could say that the square root of 25 is the same thing as saying the square root of 5 squared. Right? 25 is 5 squared, so the square root of 25 is the square root of 5 squared. All right? Now, square roots and squares, those are inverse operations. They cancel each other out. Just like we use addition to cancel out subtraction, and multiplication to cancel out division, so on and so forth, we use square roots to cancel out squares, right? And so once we have those two perfect squares in there, we can just say that is equal to 5. All right? That's equal to 5. Now, you may recall from Algebra 1 that when you have a situation like this, x squared equals 25, okay, how would you solve this equation? What should you do to both sides? Square root, right? You may recall from algebra that when you get your solutions here, what are your solutions for x?
It's plus or minus 5.
Plus or minus 5. Good, okay? In this setting, we give an answer of plus or minus 5. But when you see that root 25 on its own in the wild, the answer is just 5. Okay? The reason for that is that when we tend to see that square root of 25 just by itself on its own, we're really interested in what we call the primary root, 5. Okay? In an equation, we are interested in all the possible values of x that make that equation true, right? So when we have x squared equals 25, of course, 5 makes this equation true, but doesn't also negative 5? Of course, negative 5 squared gives you 25. And so that's why in an equation setting, when you take the square root of both sides, you want to have that plus or minus. But when you're just seeing like an expression, the square root of 25, you want to leave it just 5 as your answer there when you simplify. Okay? Also, of course, in an equation setting, sometimes you throw out the negative because it doesn't make sense in the context of the situation too, right? But that's something that's pretty easy. All right, so, but the next question that I want to ask is how do we simplify the square root of 50? The square root of 50, is 50 a perfect square, like 25 was? So no, it is not, right? There are no two nice numbers, I'll say, that when you multiply them by each other, they give you, or there's no single number that when you square it, you get 50 there. No nice number, at least. No natural number. All right. So how do we simplify some of this? Well, we can see that using some properties of square roots, okay, we can take that 50 and see that, 50 is 2 times 25. Okay. Now, of course, I also could have said the square root of 5 times 10, right? I could have said that. But which one is more helpful here? Why is the first one helpful? Why is that a helpful product to have there?
Because it has a perfect square.
It's got a perfect square in it, right? 5 and 10, neither of those are perfect squares, so it's not super helpful to break it up this way. But 2 and 25, there's a product of square roots that there's a property of square roots that if you have a product inside the square root, you can break up that square root over the product, like so. Okay? This property does not hold true for addition. This property does not hold true for addition. So in general, the square root of like 2 plus 3, for example, does not equal the square root of 2 plus the square root of 3. Okay? In general, that is not true. Not true in general. Same thing for subtraction, right? But for multiplication and division, if you have the square root of a product, that is equal to the product of the individual square roots there. Which is helpful because we can now evaluate what the square root of 25 is. We know that's 5. The square root of 2, well, can we break 2 up into any more perfect squares besides 1? Does 2 divide by any other perfect squares? Can we break 2 up into other perfect squares? Like we broke 50 up to 2 times 25. Can 2 break down any further? No, okay? In fact, 2 is what kind of number? It's a prime number, right? It doesn't break down any further at all, okay? So it's just then our answer then is 5 times the square root of 2. Okay, that's our final answer. Generally, we put the non-square root number in front, okay? Just because, I don't know, it helps with organization and stuff like that. Okay? So that's the idea there. That's one way to do it, is to kind of like look at your number that you're trying to get the square root of it and see if you can break it up into perfect squares, like we did here. Or sorry, break it up into a perfect square and another number, and then take the square root of that number, and then check the other number that's still under the square root, see if you can like break it down further. That's one way to do it. Okay, an alternative way to do it, I'll show you another strategy here. If you have the square root of 50, okay, and you just break it down using like something called a factor tree. So for example, 50 I know is like, well, let's say it's like 5 times 10. I'll do it the other way here. Okay, can I break 5 down any further? No, but can I break 10 down any further? Yeah, I can make that like 2 and 5, for example. And then 2 can't break down any further, and 5 cannot break down any further. Okay. And then what you want to do there is look for pairs. So I see a pair of 5s right there, right? And so the pairs of 5s means that the square root of 50 is the same thing as the square root of 5 squared times 2, right? 5 squared times the 2 there, which then I can say, 5 can come out since it's a perfect square. So 5 root 2 that way. That's another way to do it too, is using a factor tree to kind of help you see all the different prime factors. Okay. Another opportunity. All right, so let's try another one here. Let's simplify the square root of 48. Okay. 48. Are there any perfect squares that divide 48? Avery, what do you say?
Or 16.
What's that?
16.
16 and 3, okay. So 3 times 16 is 48. Okay. Alternatively, here we could have said something like 8 and 6. Okay, but 8 and 6, neither of those are perfect squares, but you could do it that way. I was thinking we could divide this by 4, right? 12 and 4. You could do it that way too if you wanted to here. So I'll show you either way. Okay, Avery's is the better way though because it's going to get done faster. Okay, so square root of 3 times 16 is equal to the square root of 3 times the square root of 16, which is going to be 4 square roots of 3. Okay, square root of 12 times the square root of 4 equals square root of 12 times the square root of 4, which is 2 times the square root of 12. But what can we do to 12 that we can't do to 3? What can we do to 12 there? That divides further by what?
3.
By 3, yeah, it divides into 3 and 4. So I can do 2 square root of 4 square root of 3 like that. Because 4 times 3 is 12. And then what's the square root of 4? 2 times that 2 that's there gives us the 4 root 3 that way. Okay? So you can see that you can like kind of keep going, keep looking for those perfect squares that divide into your number in the square root until you're done, until you get a prime number there. Okay. Again, alternatively, we could have done the factor tree thing here. So like I know 48 divides by 2, that leaves me 24. 24 divides by 2, that gives me 12. 12 is divisible by 2, gives me 6, and 6 is 2 and 3. And then all of these are prime. I see one pair, two pairs of 2s, okay? And so then I'm going to have, those are going to be 2 squared. So alternatively, I could see, aha, it's going to be 2 squared times 2 squared times 3. 2 squared, and a 3 there. Okay, and so that's 2 times 2 times the square root of 3 that's left over, 4 square roots of 3. Okay, another alternative. All right, questions on any of that? So let me give you guys something to try then. Okay, so you guys try these 3. So simplify 1, the square root of 63, 2, the square root of 42, 3, the square root of 192. Okay, just give those 3 a try there. So, should have something like this. Okay, I did it a variety of different ways there. 1 is 3 square roots of 7. Okay, 2 square root of 42. Can't simplify. Can't simplify. It's just root 42. There's no perfect squares that you can divide root 42 by. Okay, except for 1. Doesn't really help though. And then 3, I did the factor tree method there, and you should have gotten 8 square root of 3. Any questions on any of those? All right, we'll shift gears here a little bit, talk about the Pythagorean theorem and then the Converse Pythagorean theorem. All right, but first I just want to briefly re-mention the anatomy of a right triangle. Okay, I believe you guys already know. The names of these things, but we'll go over them again. Okay. This side right here, segment AB, we call that the what of the right triangle? hypotenuse. Okay? AC and CB together are both known as the what? That's the hypotenuse. CB is a what, and AC is a what? They're called legs. That's a leg, and that's a leg. Okay? They're the sides that are adjacent to the right angle. Okay? Of course, we know that, A plus B plus C, that's going to be equal to 180 degrees. But since our triangle is a right triangle and angle C is 90 degrees, what does that mean A plus B have to be? A plus B. A plus B has to be 90. A and B don't have to be 45 necessarily, right? A and B will be 45 if the legs are congruent, right? If that leg and that leg are the same, then A and B will be 45 each. But for now, A plus B equals 90 degrees. And what do we call two angles that they add to 90 degrees? Complementary. Complementary. Exactly. Okay, so it's super important to remember that the non-right angle, the two non-right angles in your right triangle, they are complementary to each other. Always in a right triangle. Always. Always. Okay? Alright. So let's take a look at the Pythagorean theorem here, even though you guys know it already. Alright. And then we'll also quickly discuss the converse too. Okay, and I won't then waste our time with doing too much of that. So we'll just do like maybe one or two problems here. So Pythagorean theorem. Okay. I want to be careful here with we're not just going to state, A squared plus B squared equals C squared, because that is true. Okay, that is true. But I wanted to make sure that we're of course a little more careful here. So, given right triangle, given a right triangle, with sides A, B, and C. C is the hypotenuse. Okay. Then A squared plus B squared equals C squared, right? Oh my gosh, I'm off the screen. Sorry about that. Okay. Given a right triangle with sides A, B, and C, C is the hypotenuse, then A squared plus B squared equals C squared, right? That should not be a surprise. We all get that. No big deal, okay? But I just want to make sure, first of all, Pythagorean theorem only applies to right triangles, all right? Again, for this unit, all the units we've been working for in the past, we've been working with all sorts of triangles, right? This unit that we're going to be moving into on Wednesday of next week, again, Monday is going to be review day, Tuesday is test day. The unit we're going to be moving into on Wednesday of next week is all right triangles. All right triangles. Okay? So I want to make sure that we're cool with that. Okay? That's Pythagorean theorem. The converse of the Pythagorean theorem, then, is the reverse of that. If C squared equals A squared plus B squared for a triangle with sides A, B, and C. C is the longest side. Then the triangle a right triangle. Okay? So if c squared is equal to a squared plus b squared for a triangle with sides a, b, and c is the longest side, then the triangle is a right triangle. Okay, so c squared equals a squared plus b squared, right triangle. Okay, what happens though, that's not always true, right? So what if we take the longest side in a triangle and we have that c squared is less than a squared plus b squared? What kind of triangle do you think that's going to be? Will it be right? No. Acute. Why do you say acute?
If c squared is less than.
So c squared is like too small for what it should be to be a right triangle.
Because like since c would be the smaller side, then the angles.
It wouldn't open up. Exactly. It would be smaller than a right angle. Exactly right. If c squared is too small, right, c squared is not equal to a squared plus b squared, it's less than that, then we have, exactly right, it will be an acute triangle. Okay? And so then if we want to be able to identify an obtuse triangle, what can we write here? C squared will be what? Greater than. C squared will be greater than a squared plus b squared. That will indicate an obtuse triangle. Okay? So the converse of the Pythagorean theorem has, a different kind of way we can go with it. Pythagorean theorem relates all three sides of a single triangle, but the converse allows us to then take that relationship, c squared equals a squared plus b squared, and use that not only to identify right triangles, but also acute and obtuse. The key here, though, please don't miss out on this, the key here is that c is the longest side. C is the longest side, so please make sure you use that longest side. Okay. So we'll just do two examples here, and I'll just have you guys try these on your own here. Let's see if I can make it nice. Yeah. Okay. So I'll give you two examples here to try. All right. And you're either going to use the Pythagorean theorem to answer it or the converse of the Pythagorean theorem to answer it. So be prepared for that. Okay, so for the first one here, I want you to solve for x. Solve for x. And number two. So one may not be what you would expect for a Pythagorean theorem problem, but I promise you it does involve using the Pythagorean theorem. Okay. Please simplify your answer to simplest radical form too. Okay. Please simplify your answer to simplest radical form. So no decimals, please. Simplest radical form, please. Emily, can you help us out for number 1? What was your
I
setup
said
here? What'd you do?
12 squared equals 4 squared plus b squared.
12 squared equals, you said,
4 squared plus b squared.
okay, plus b squared. Okay, so let's see here. We see that we have a right triangle in here. Okay, 12 certainly is the hypotenuse of that right triangle, right opposite the right angle there. How'd you get 4 though?
I took like the total length, which is 10, and then I subtracted 6 from it.
Right, so this little piece right here has got to be 6, right? Because this piece over here was 6. And so then that leaves this to be 4 right there. Very good. And this dotted line, well, that's the same as the x right there, or the b is what you put there. That's fine. Okay, so 12 squared, that's going to be what, 144, right? 4 squared is 16. Subtract 16 from both sides. We can get b squared is, what is 144? Take away 16?
128.
128. Okay, and then square root both sides, right? Okay, so b equals, okay, so 128 is not a perfect square. Were you able to simplify the square root of 128 at all?
I just like calculated on my calculator. I said it was 11.3.
Okay, so approximately 11.3. All right, but let's see if we can break that down because we know how to simplify square roots now. All right. So, well, it looks like it breaks down. We can divide it by 2. That's not very helpful. Maybe we can divide by 4, though. Let's see here. 128 divided by 4. Yeah, it looks like it would be 32. Right, like that. And so that gives us 2 times the square root of 32. But 32 is also divisible by 4. It's square root of 4 times the square root of 8. So that'll be 2 times 2 there. So it's going to be 4 times the square root of 8. But 8 is also divisible by 4, so it'll be 4 times the square root of 4 times the square root of 2. And that's going to be 2 times the 4, so we get 8 square roots of 2 for our precise answer there. Okay, for the precise answer. Or 11.3 for the rounded answer. Okay? We should be prepared to do either situation here. Either giving me the decimal or the simplified version. Okay? So please be prepared to do either one. Okay? The directions may ask, put it in simplest form, in which case you will need to give this, and not 11.3, right? That would not be the final answer if you're giving it in simplest form. Okay? Questions on 1? Yes, Madison.
That's 7, and that's a square root of
You got 7 times the square root of 2? Well, how did you divide up your 128?
I did 128, 4, 32. And then
Okay,
4
you did like the
gets-
factor tree?
Yeah.
Okay, 4 and 32.
4 gets 2 twos.
2 twos, okay.
32 gets 4 and 8.
4 and 8, and then 4 also is 2 and 2
And
there.
the 8 gets 2 and 4.
2 and 4.
And then the 4 gets 2 and 2.
2 and 2. Okay, so I see 1, 2, 3 pairs of 2s. So that's going to be, let's see, I'm going to run a space here. I'll do it right here. Okay, so the square root of 128 is equal to 1, 2, 3. So it's going to be 2 squared times 2 squared times 2 squared times, and then the leftover 2 there that doesn't have anything.
Oh.
So it'll be 2, 2, 2. It's 8, and then the root 2 there. You see where you
Yeah,
mean?
I just skipped that step by accident.
Okay, gotcha. Yeah, so, yeah. And you can skip that step. You don't need to write this out. You can just see, okay, I got 1, 2, 3 pairs of 2s, so that's 2 times 2 times 2. It's going to be 8, and then the leftover 2 there will be left in the square root.
I just counted the...
Miscounted. Gotcha. Okay. All right. Glad we figured that out. Other questions on number 1? Aubrey, were you raising your hand earlier? Are you okay?
No, I got it, yeah.
Got it. All right, number 2. Okay, we got 3 different scenarios here to classify these triangles using the sides. Okay, so let's go to Stephen. Stephen, the first one, I guess I say, not number 1, but the first one here. Were you able to classify this triangle?
I said it was obtuse.
You said it was obtuse. Okay. What was your setup here? What was your analysis to help you figure that out?
Oh, I just guessed for this one.
You just guessed.
Yeah, I just.
Okay, well, you guessed wisely, okay? But let's make sure that you don't guess poorly in the future. Here, we want to figure out how to do it, so we'll go to our little analysis up here, okay? Which one of these 3 sides here, Stephen, is the only candidate for C? Like, which one would C have to be?
14.
The 14, right, because
Yeah.
the biggest side. So let's say 14 squared. I'll go ahead and do the 5 squared here, the 13 squared here, okay? 14 squared is, I don't know off the top of my head. 196. 5 squared is 25. 13 squared is 169. 25 plus 169, I'm going to run out space here. But that's going to be, let's see, 174, 194. The c squared is ever so slightly bigger than the a squared plus b squared, so this is in fact an obtuse scalene triangle. Okay. All right, we'll go to someone else for the next one here. Thank you, Stephen. All right, how about Madison B?
I had a right triangle.
You had right triangle, okay, and that is correct. It is a right triangle. Okay, it does fit for the Pythagorean theorem there. Okay, very good. And let's go to Preston. Preston, for the third one there. What kind of triangle did you get there?
I said it wasn't a triangle.
Very good. Not a triangle. Preston, how'd you get that?
Well, 6 and 8 together don't equal 20.
Right, right. So remember, folks, right? We can't let the new stuff push the old stuff out of our brains. And if you remember, we had that triangle. I think it was called a triangle inequality theorem. But either way, where any two sides of a triangle have to add up to be greater than the third side. 6 plus 8 does not add up to be greater than 20, so it is not a triangle. Does not exist. Okay, cannot exist. All right. Questions on any of that? Okay. Well, ready to get you guys started on your assignment here. And so what I've got, it's actually on the Google Classroom. It's 2 papers. Okay. So the first paper is like simplifying square roots. I'd like you to do all of that. Okay. There is some like it's one of those like coloring in papers where you like color certain parts or a certain way for your answers. You don't need to do the coloring part if you don't want to. However, if you want to do the coloring part, I have printed out physical copies for those of you that like to do those kind of like shading in stuff like that and see the picture of the design that comes out. The second paper, okay, is like stuff with the Pythagorean Theorem. Okay, and the Converse too. And for that one, just do the odds, okay? Don't do the evens and the odds, just do the odds, okay? Because I don't want to like overload you with too much here, okay? So simplifying square roots, I do want you to do the whole thing there. It's just the front. And then Pythagorean Theorem, Converse, I want you to do just the odds for that worksheet, okay? And that's all on Google Classroom. Okie dokie. And then I'll pass out those physical copies if you want to do the shading and stuff like that. Let me just get this situated.